Good morning, everyone. Today we are in the second day of our technical talk series, and I'm Kumar Apurv, and I will be the moderator for today's session. The next speaker, our Mr. Manu Joseph. He is the supply chain expert, as well as he's as somehow I'm getting the
There's an echo, guys.
yeah. Yeah, if you're not speaking, please go on mute. That would be helpful. Yes. So Manu Joseph comes with a rich experience in supply chain, and he also has a very good experience in machine learning. His keen interest is in natural language processing too. Yeah. In the today's session, he will be talking about or walking us through his experiences on handling large-scale time series forecasting models. Right, we all have faced these issues with when we do the forecasting. Is that it's very simple when we do the forecasting at say 1,000 of SKUs, but when it comes to 1 million or more than that elements, the forecasting becomes very challenging. How should you structure your thought process and make your time series forecasting work an art? And that is where you require some help from the experts like Manu Joseph. So Manu Joseph, it's all yours.
Thank you, Kumar. Thank you for that introduction. And good morning, everyone. So like Kumar mentioned, we're going to talk about demand forecasting, not just demand forecasting, but demand forecasting at scale. So let me just start off with a quote. So Paul Sappho has put it perfectly that we're not just generating a forecast for just forecast's sake. We're generating it to enable somebody to make some action like today. And with that, I also want to set the tone of the session. This is not going to be just another theoretical exposition on IDMA or exponential smoothing, but it's going to be more of a practical approach on how to deal with real world problems. So let's just set the screen, set the stage by looking at this video, which kind of explains what demand forecasting is and why do we do it.
What if you can predict the future? For example, predicting demand for smartphones or availability of beds in a hospital, availability of hotel rooms. Accurate demand prediction converts to big money for businesses. This is a common challenge across industries. Let's choose the bike demand prediction as an example use case. Bike sharing companies have thousands of bikes and hundreds of bike stations across each city. Each station has a fixed number of docks for parking bikes and a variable number of bikes available at any time. Real-time dashboards show the problem, but it's too late and expensive to resolve the problem by rebalancing the bikes. If only bike operations could predict the demand per station per hour. So in today's demo, we'll show you how this can be solved by applying big data.
Yeah, so let's just ignore the last part. That's not the demo. What we are going to look at today is this. We're just going to have a brief look on a common terminology which is in the demand forecasting space. Then have a high-level introduction about a few demand forecasting techniques. Then we look at how we can apply them at scale. We also look at how we can segment our time series so that we can have targeted actions for them in an automated way. And then to wind up the session, we also have a brief look on how we can adjust our forecaster models in the troubled times like we have right now. So we'll have a few specific question breaks where we'll pause the session and take a few questions from the audience and try to answer that. All right, and with that, let's clear the air with a few terminologies. So demand forecasting. So this is basically in our example that we just talked about, right? The bike demand prediction. So if you're forecasting the bike demand for a particular station for the next, say, 6 months, that is what demand forecasting is all about. And another terminology that is commonly, thrown around in these circles is demand sensing. So demand sensing is like a very niche application of demand forecasting. So in our example, for in our example, right? So if you want to do a prediction for all the stations, what's happening in the next 1 day or 2 day in a very short term. And for that, we use variables or features like your train timings or the app registrations. So things that can sense the endpoint demand. So once we include such information into the modeling process, then it's kind of called demand sensing. And there's another term which is commonly heard and often confused is demand shaping. So I've heard this being confused with demand sensing or demand forecasting, but so demand shaping is a totally different thing. It's nothing to do with forecasting per se. So demand shaping is more like a set of strategies that a company adopts. So in our case, for example, the bike company, so if it decides to provide a percentage of or a price incentive on non-peak hours, that's a strategy that they adopt to level the demand. So those kind of strategies are demand shapings. All right, then let's just move on to the journey of forecasting. So forecasting is a journey. So there are multiple stages in your journey, and we as a company have seen clients in all of these different stages. So we've helped them move from univariate forecasting to multivariate forecasting, and we've helped them move from multivariate to automated forecasting. So it is the essence of all of those interactions that we are kind of distilling into the session that's coming up. So to start off with, let's just take a few techniques from the demand forecasting world and have a high-level overview about it. So if you want to classify the different techniques that we can use for demand forecasting into two, it's going to be like one set of methods. The time series models are a set of methods which take time as an intrinsic part of the model. So it is modeled in the formulation of that model, right? So things like your ARIMA, exponential smoothing, profit, recurrent neural networks, all of these takes time or sequence into the modeling framework. And then we can have general regression methods also applied to time series. And in that case, we'll have to inject time as an external dependency. So we'll have to do additional features to make it work. So a few examples are lasso regression, gradient boosting machines, and neural networks, your normal neural networks. So let's start off with the time series set of models. So I'm not going to bore you all with the traditional the things that you've heard a million times, ARIMA, how you do a PACF plot, and how you do exponential smoothing. So I'd rather focus my attention on a few newer and more sophisticated methods. And first on the list is profit. So that's a newer algorithm, which is more closer to machine learning than classical learning. And this has come out of Facebook research. So in the profit formulation, it's a generalized additive model, and it postulates that your demand is like an additive component of a trend, a seasonality, and holiday effects. And whatever is not modeled into these three is kind of bundled under error. So in the actual implementation, this is also extended to additional regressors. So you can have, like you extend ARIMA to ARIMAX, you can extend this also with additional regressors. And the trend, so there are two options in the trend. So it can either be a linear trend or a logistic trend. So there are some things which do not increase forever. So for that, we have a logarithmic curve or a logistic trend for that. And seasonality is modeled using Fourier features inside. So so there is daily, weekly, yearly, and all monthly seasonalities built into the model. And holidays are more like regressor effects of different holidays, and all of this combined gives you a very robust model, or a very like kind of working out of the box kind of a model. And it's very robust to outliers. It handles missing data automatically. And even if there are like dramatic changes in your time series, for example, your time series has an upward trend and suddenly it reverses. So that is also kind of automatically figured out. So it has an automatic change point detection, and it determines the places where the trends change drastically and then fit piecewise trends so that the whole thing works well together. So all of these innovations that Profit has brought in gives us a very reasonable forecast, even if it's on a messy data with little to no manual effort. So, and that's like great news for a beginner. And if you look at how we can implement this, that's even simpler. So you just need to read in a data frame. The only thing that Profit tells you is you just need to have one column with dates in it, and it should be named DS. And there should be another column which has the historic actuals in it, and it should be called Y. Once you have this, that's it. You read the data frame, pass it, initialize the model, fit the model, and tell it that I want to do forecasting for the next 35 days or 365 days, and then make the forecast. That's it. So it's as simple as that. So from Profit, let's move on all the way on the other side, which is a lot more sophisticated than Profit. So this is from the neural networks world. So recurrent neural networks is a kind of architecture which is defined or designed to handle sequential data. So this is how you typically see it represented everywhere. So there is a box A. For now, let's consider this box does something magical. It just takes in two things, my previous state or a state and a current input, and it provides another state. That's something magical that it does. So now what we do is we have a sequence of data. Right? Time series is nothing but a sequence of events or sequence of values. So you have x0 to xt. So we take this box A, we start passing x0, and it'll give us an h0. H0 is a state, and we pass this h0 and the x1 to the same box again. We get a new state, and we continue this process till the sequence is ended, right? So by doing this process, what we are essentially doing is we are encoding the information in the sequence into one single state. So this h, which is updated at each time step, is like has the information of the entire state. And once this entire thing is done, we'll just take that ht or the last state, and we'll use that to do forecasting, like put a feed forward neural network on it or train for a forecast. So that's the general process that we have in RNNs. And if you want to look inside A, in a vanilla RNN, the operations inside is pretty simple. Just take the previous state, you get the current input. You concatenate it, pass it through a neural network, a feed-forward neural network, apply a TANH activation, and then you get a new state. And this is getting repeated across different time steps. But nowadays, typically hardly anybody uses vanilla RNN anymore because of a lot of problems which were kind of brought out in the early 90s. The main ones are like vanishing gradient. Because of that, it stops learning. So to overcome those problems, a newer architecture which has the same essence, but it does it slightly differently. So newer architectures like LSTMs or GRUs. LSTM is long short-term memory, and GRUs are gated recurrent units. Both of them are recurrent neural networks, but slightly different. So this particular diagram on the right, this is basically what happens inside the LSTM. You can see that there is a lot of operations inside. So it's a little bit more involved than RNNs, but intuitively what you can see is there is just one line on the top which goes unhindered from a cell to the next cell, right? So that's kind of like the memory that it has, and all the operations that you see here, all it is doing is deciding what to remember and what to forget. So this is how the recurrent neural networks kind of work, and it actually works very well in practice if you have a long time series. Now that we have looked at a couple of time series methods, let's also look at how we can apply all of our general regression to a time series. Because that once you've made that jump, right, you've actually opened up your repertoire into a huge variety of algorithms. But it's not straightforward because time series and regression are two fundamentally different problem paradigms. So if you look at time series, it's the problem is basically I have a sequence of numbers. I have 1, 0, 1, 0, 0, and then what is going to be my next value? But if you look at the supervised framework or the regression framework, we have pairs of values. I have when x is equal to 5, I have 1. When x is equal to 6, I have 0. So I use these pairs of values to kind of find out a relationship or a function which transforms my x to y. So these two are fundamentally different, right? So we need to do something to the time series to make it fit into this particular framework, and which is one of the methods is called the sliding window method. So you fix a window 3 or 4, depending on the problem. And then what you do is you say that T1, T2, T3 are my X and T4 is my Y. So I'm using T1, T2, T3 to predict T4. Then I move the sliding window 1 to the right. You get T2, T3, T4 to predict T5. And then you repeat that process. So once you've done with moving the window across the entire time series, you're generating different samples of data for the supervised algorithm. So then you can just basically apply a linear regression or any of these regressions on top of these this transformed matrix, and you're good. But then using the just the sliding window, just the lags is a very rudimentary way of doing it. But if you want to get good performance or equal performance as other methods, you would want to help your model learn the time much better. One of the main things is daytime features. So things like day of the week, month, quarter, month end, season, all of these things help the algorithm or the model, the regression model, learn seasonality really well. And then we have the lag features that we just discussed, which is from the sliding window. And we can also use the sliding window to create rolling mean features. So instead of giving T1, T2, and T3, we can also give the mean of T1, T2, T3 as a feature. Then we have trend features. So trend is something really intrinsic to the time series model or time series setup. But regression models are not really equipped to find out the trend as it is. So we'll have to do some kind of adjustment, or we have another simple linear model to get the trend out and provide that as a feature. And then the daytime features that we discussed for capturing seasonality, right? Sometimes it's beneficial to use Fourier features for Fourier transformations on those features to get continuous representation of seasonality, which will also give you a boost in your performance. So now that we have made the transition into from time series to regression, I also want to touch upon a few brief problems which is commonly occurring when you're doing this kind of setup. One of the main things is temporal data leakage. Data leakage, you all know, right? So when your target kind of leaks into your input and the model starts to exploit it. That's not a position that anybody wants to be in. And temporal data leakage is similar thing, but on a temporal concept. And it's typically hard for an ML person because the majority of in the domain, the majority of the problems are cross-sectional in nature. And to think about it in a temporal way is a slight change in paradigm. One of the most common example is cross-validation, which is a really popular technique to avoid bias variance trade-off, right? So the first instinct of an ML person will be to use a k-fold validation. But the problem with that approach is when you're dealing with temporal data, you'll need to respect time when you make your cross-validation splits. So you can't use future data, train on it, and then predict on the past. So that's kind of like cheating. So in the Python world, or in the sklearn world, there is something called time series split, which is like a drop-in replacement for k-fold validation. So you don't need to learn any new code. You just need to replace what you call and put another one in it, and it kind of starts working. So when you're starting out and when you're not sure about, not entirely sure about what you're doing, I'd always suggest to keep or stick to time series split when you're dealing with temporal data. Another common problem that is typically seen is when you're making lag and rolling features, your target kind of has a tendency, we will make an error to kind of make it into a leakage. So especially when rolling features are happening, right? So in pandas, you have a rolling mean or rolling window function, right? So by default, it kind of includes the current time step also, which is like a direct leak of your target into the rolling mean. So to avoid such situations, I always suggest to at least shift it by 1 and then start applying a rolling feature so that you're absolutely sure that your target is not leaked. And one short way of finding out whether you have target leak is that if you think your CV scores are too good to be true, it is, your suspicions are right. Then another common problem or a practical problem is that when you want to have multi-step forecast. So all of your traditional methods or even Profit, we can just tell the model that I want a prediction for the next 5 months. It'll just give you for next 5 months, right? But in a regression, like most of our regression methods have only one target. So you can only do it one step at a time, right? So then how do we do multi-step forecasting? So one of the strategies is called rolling forecast. So we basically train a single model to predict one step ahead. And once you make that one step, we consider that forecasted value as the actuals. You adjust our lags and rolls and everything. Then you pass it through the model again to get the next and the next. So then you repeat that iteratively. So the disadvantage for that is that you're actually kind of propagating the error that you make in the first time step into subsequent time steps. So the forecast will be worse as you move far away from the current time. There's another way of dealing with this, which is when you have direct forecast. So you have one single model which predicts t plus 1. We have a separate model which predicts t plus 2 and another one which predicts t plus 3 and so on. So this is also a good way of doing it, but not without disadvantages. Suppose if you have 18 months to forecast, you have 18 models to manage. So then there is another way also, which is typically can be used when a regressor supports multiple targets, which is usually the neural network world. So then you can have the past observations, train them, and then do direct prediction for t plus 1, t plus 2, and t plus 3. So that is kind of the kind of multi-step forecasting paradigm that we should be adopting, right? Yeah, so this is our right time to kind of take a break and see if there are any questions. Kumar?
Yes, can you hear me?
Yeah, we can hear you.
All right. Yeah, this was very fantastic that you explained all the things. We have two questions. One from Naman. He is asking, once you convert time series to regression, doesn't it becomes a cross-sectional problem? And the another question which he has also attached it with is, time series split is still necessary? That's the question from Naman.
Good. Yeah. Let's take that. Good. It's a good question because it's an area which is slightly debatable. So there are active research going on both sides. So there are papers which say and prove that time series split or that temporal validation is the way to go. And there are papers which prove even if you do cross validation k-fold, it doesn't matter. So since that is a debatable topic, right? I mean, unless you're really sure about the dynamics of the different features in your model, it's safe to actually do the time series split.
All right. So hope that answers Naman. Yeah, there is one more question, and that is kind of slightly generic, but yes, that's the question usually asked. What is the difference between classical and ML and DL based forecasting? This is by Sachin Sarma.
Okay, all right. So yeah, so there are a few differences. So classical methods, right? So most of them have like it's based in statistics and by extension have strong assumptions about the input data. It needs to be IID. It needs to be in a Gaussian distribution. So all of those things. But some of most of the newer age methods kind of glosses over that strong assumption. Even if you don't have a really strong, even if you don't satisfy the strong assumption, it is still possible to get good enough forecast for that. And then another key difference is all of your classical algorithms typically use a single, as in just historic data, with an exception of few like VAR and IDMAX. So the newer age of algorithms is more truer to the environment around us because it focuses on the causal factors more than the older ones. And the last one is probably the newer ones, right? It have much higher capacity to learn complex patterns, have a large degree of freedom than our classical models, which is a double-edged sword if you think about it, because it's also easy to overfit to a particular pattern, but it can also learn a new pattern as well. So yeah,
that's right.
Is kind of
Yeah. So these were the two questions we had so far. I think if there are no other questions, then we can move to the next section.
All right, cool.
All right.
All right, so let's just start into the main subject at hand, which is how we do forecasting at scale. So if you look at a typical data science process, so you start by asking an interesting question. And in our case, the interesting question is, how many bikes do I want to keep at this particular station at this time? So then you go and collect all the data that is necessary, your historic records of your bike sale or bike hires, and any other demand signals that you can get your hands on. Then you start exploring the data, right? You plot the data to find out whether there is a pattern, whether there's a trend or a seasonality. Are there any outliers? So you have this exploration, do the corresponding corrections and transformations necessary. Then you start modeling the data. You build a model, you validate it, you see if this is not working, you change something, you do build another model. And once you're satisfied with it, you communicate and visualize the result. Now, in our case, right, just imagine that me as a company have now expanded to the entire world. So now I want to do forecasting for all the stations everywhere. So that can easily come around to a 1 million stations. So if you have that scale, that amount of scale, how do you follow this process? Can you really plot the data and find anomalies and patterns anymore? Can you really validate each and every model and make decisions on it? And can you really engineer specific features for each model? So the only way that you can handle the scale is if you embrace automation. And one of the key processes or kind of the key stages in the data science process is model selection and hyperparameter tuning. So typically in an ML workflow, right, we use hyperparameter tuning on a daily basis, and our default choice is grid search. And if you think about it, you can easily extend your grid search to a model selection plus hyperparameter framework as well. But then, yeah, so let's just talk about grid search. So you have a hyperparameter 1 and 2. So what you do in the grid search is you make the entire grid, all the possible combinations between these two. You evaluate your model in each of these blue dots and pick the best one. That's like a sure shot way of getting your best model possible, right? But this is not really computationally feasible, especially when you're doing it at this scale. So there is another method that is like another popular method, which is random search. So which basically does is more like a shot in the dark. So you randomly pick a few points from these blue, check if the model is working on in all of those, and pick the best from that. So if you think about grid search as sweeping a room from one corner to the other corner methodically, random search is more like switching off the light and then picking a few spots in random to kind of clean and hope that we've got the dirt. But there is a middle ground. Imagine the light is still off, but you have a flashlight. So with the flashlight, you can look at a couple of places and see, okay, this particular area has more dirt. Let me start sweeping there. So that middle ground is what we call as Bayesian optimization for hyperparameters. So let's look at take a small example to kind of understand what's happening. Let's imagine that we have 3 parameters, A, B, and C, and using this we have a function, and we need to minimize that function by the optimal values of A, B, and C. So in a grid search framework, right, how we start off is A. So let's take A, and this has a range of 10 to 20. B has a range of 20 to 30, and so on. And then we start evaluating, right? So instead of that, in the Bayesian optimization, we define probability distributions for each of these. So you have a distribution for A, B, and C. It can be as uninformative as a uniform prior. So it says that it's equally likely to be 10 or 20. Or if you already have an intuition that, okay, 15 is going to be my right value, but still I want to search around it. So you can define a Gaussian distribution centered on 15 with a standard deviation around it. So these probability distributions are called the prior belief in the Bayesian world. And now that we've set these prior belief, we sample 3 parameters from these distributions. So now we have a value for A, B, and C. We put this thing into the function. We get the loss or the metric, and based on this metric, we update our distribution of the 3 parameters. So this is called the posterior belief. So this process we repeat n number of times, that n that we set, and each iteration kind of sharpens the posterior and slowly moving towards the optima. So by doing this process, right, what we are doing is, so if we have a particular minima here, we will concentrate our search here and not here. So because of that, we save a lot on computational resources that we waste on places in the or spaces in the parameter space, which is not useful. And we get a much better convergence rate. And another thing is this also lets us gives the control to the modeler to decide how much time he wants to spend in doing hyperparameter tuning. Okay, and another way, so basically one of the key libraries that we use internally in our projects for hyperparameter tuning or Bayesian optimization is Optuna. So how this is different from its predecessors like HyperOpt is like it has eager search spaces. So previously in HyperOpt, we used to define all the search spaces before running in static dictionaries. But here in Optuna lets us do it on the runtime. So it's much more Pythonic and imperative than the HyperOpt kind of way. And another key thing is that it has efficient pruning implementations. So by pruning, so if you know what early stopping is in the neural network world, pruning is similar in the Bayesian optimization. You stop a trial before it goes forward, or if it is unpromising, you stop it midway. And the good thing about Optuna is it has ready-made integrations to all the major machine learning and deep learning libraries, so that it's very easy to implement pruning. And if you look at the code sample, right, you'll understand how easy it is to implement the Optuna. So just need to define a function, which is the objective function, which takes an argument of trial. And this trial is what you use to generate your parameters. And then you return the value of that parameter. Here it's x minus 2 the whole square. We want to find the value that minimizes that. And the only thing that you need to do is you need to create a study and then tell it that this is the function that I want to optimize. And this is the number of trials that I want you to do. That's it. And then it'll run its course and give you the best parameters for that. And another way that we can handle scale is by using pooled models. So in our case, right, instead of having individual models for each of the station in the world, we can kind of take an assumption and say that this particular region should behave similarly because it has similar demographics and similar workplaces and work routines and things like that. And we can have a single model do a bunch of related time series. So so when you go from 1 million models to say probably hundreds or thousands of models. I mean, if you think about the engineering nightmare of managing 1 million, the training time required, the resource utilization required, then this is like a huge win. And also there is a modeling advantage as well. So if you have a small time series, it may not do well. Small time series as in a short time series. It may not do well in isolation, but when it is pooled with a lot of similar time series, right, it kinds of starts to do better. Okay. And another key aspect in managing scale is your ability to kind of segment your time series, different time series into buckets, and have targeted actions for those. So one of the classical way of doing it is using a heuristic. This is a heuristic which is very popular, really popular. So you have an average demand interval. That's something that is like a proxy for your intermittency or how sporadic your demand is. Then you have something called coefficient of variation, which is like a proxy for your variability in the series. So if something is really continuous, as in there is no sporadicity and very low variability, it'll kind of fall in the smooth bucket, which is the easiest one to forecast. But unfortunately, in like most of our real world scenarios, you hardly find anything which is smooth. You'll mostly find things in erratic and lumpy being the hardest to forecast. But then we have different methods or different kind of methods which is specifically tuned for each of these separate sections so that it kind of makes do with the best things that it has. So apart from the heuristic-based segmentation, there's also a few methods of scientific methods of clustering time series. So you must have heard of normal clustering, right? You have k-means and all that. So in k-means, what you do is you find out the distance between 2 points and use that to actually find the distance intuitively. So in a similar way, we can use Euclidean distance in time series. So instead of having a point-to-point distance, we are finding out a distance between two time series. So we can actually calculate the distance between these 2 points after aligning them. And then intuitively, the sum of all of these distances is the distance between these two time series. But the problem with this approach is that it only works for equal length time series, and it is also sensitive to time shifts. So if you or me look at these two curves, right, it is kind of similar and it should be, clubbed in as same. But because of this misalignment in the spike, right, the Euclidean distance will tell you that it is dissimilar. And that's why there is another classical algorithm, which is called dynamic time warping. And the dynamic time warping distance, what it does is it first has a internal dynamic programming approach, which kind of aligns these different points in the two time series as best as possible. And once that alignment is done, the calculation or the distance calculation is done on those aligned time series. So while this is shape based, it is computationally expensive, because if you have a very long time series, calculating DTW will take forever. And even though there is soft DTW, which is a faster approximation, even then it takes a long time to complete. And there are a few other methods from the newer stables of deep neural networks, where we use an auto encoder. So if you look at here, the diagram on the right, so you have an input sequence. You pass this sequence into an encoder. So the encoder can be an LSTM or a CNN or even a feed-forward neural network or a transformer, and you get an encoded representation. Then you put a decoder on top of that. Then you get a reconstructed sequence. Once you've defined this network and train it, right, then you have a very good mechanism of taking in a sequence and getting a encoded representation which is true to its initial input sequence. Then we just throw away the decoder and the reconstructed sequence. You take the encoded representation, pass different time series through this encoder, get the encoded representation, and then apply k-means or any other clustering on top of those encoded representation. So in the Python world, TS-learn is a library which implements a lot of their classical time series clustering, and autoencoders can be coded using any popular DL frameworks, or just look it up in the GitHub. It will get a ready-made implementation most probably. Right. So now this is another place that we can just take a small break, take a few questions, and move ahead. Kumar.
Yes, Manu, I think this was very informative, especially the segmentation and the clustering which is required to handle the scale of the time series forecasting models. There are a few questions. Some of them are generic in nature, and we can take that at the end of the session. However, there is one or two questions which we can take, which is relevant for the topic which we covered. And one of them is, I think some anonymous person has asked this. In pooled models, how does the model know how to predict different time series differently? If you can touch upon that. I know that we did discuss a bit, but if you can.
Yep. Got it. So when you're doing a pooled model, right, you'll also have to give the algorithm a few different features to tell what a unique key for each time series, for example. So in our example, it can be something like a station ID. Right, but there is a downside to that as well. So that if you're including the station ID and then that's a categorical value, right? You'd have to encode it. So if you're using one hot encoding, you will get 1 million features easily, which is not feasible. So then there are other ways of handling it. So there are methods of target mean encoding stable. So we kind of use the target to kind of get a single number representation for each category and use that in our algorithm. And especially when you're dealing with 1 million and this scale, right? There's another thing which works really well, which is categorical embeddings. from the neural network world. So you can so if you so it takes a page out of the word embeddings from NLP. So instead of having each word as a separate feature, a vector representation, we can train a model to have a vector representation for each of the category or each of the station IDs in this case. So then that will give you a good representation, and then you can use it in your models.
All right. Yeah. There is one more question, and okay, so person is asking, the deep learning algorithms are quite complex. Does it really have an edge over classical algorithm? Is it worth the pain? This is by Meher.
Okay. Okay. All right. Yeah. Good question. And the so in the forecasting world, at least a couple of years before, this was a point of contention. I'm not sure whether you all know that there are yearly contests, something called Meriakiris, I think that's full name is. That is M2, M3, M4, and M5 competitions, which happens on every year. So the whole point of those competitions is to fuel the research in time series space. So till about I think M3, your classical methods were doing very well. So there's a method called theta method, which won the M3 competition, and beating all of the other machine learning or deep learning or whatever that you have that time. But so if you look at the last year's contest, that M4 contest, things have started to change, probably because machine learning and deep learning are slowly maturing. So in the M4 competition, the winners were hybrid approaches. So you kind of mix the deep learning world and the classical world together, and then have a forecasting methodology from it. And after the M4 competition was closed, there were a few other researches that were happening. There's another algorithm which came out at least probably a year or two, which is NBeats, which is a neural. That's a long name, but yeah, NBeats, and that is like a purely deep learning based algorithm, which has beat all the other algorithms in the M4 competition. Yeah, and currently in M5 competition is happening as we speak. It's on Kaggle. So there it's basically right now till M4 it was always univariate time series. I think right now they have kind of moved into a multivariate kind of a scenario, so that it's more closer to the real world situations. And I'm really excited to see what happens or comes out of M5 this year.
Right. There is one more question if we can take, and that is a question by again an anonymous person. Which is the best model for demand forecasting? That's the question.
Okay. Yeah. So yeah, there is something called no free lunch theorem in the machine learning or in this field, right? What it says is, as the name suggests, there is no free lunch. So there is no one problem or one model which will work everywhere. Although by looking at our gradient boosting machines, we might think that that is the best one everywhere. But there are places where, at least I've seen, even an SVR and even linear SVR beating out XG boosters of the world. So yeah, so which model to choose, and that is basically something that you will learn through experience to have some intuition about it. But that's at best that's it. That's an intuition. So
that's right. That's right. I think it's that is the job of the machine learning experts or the data scientists, that they have to fit the models on the different problems and then see what's working better for that. There is no direct answer for it. Yeah, that's right. You said.
Yeah, true.
All right. I think there are some generic questions, but we can take that at the end of the session.
At the end of the session.
So we can,
All right. So then let's get into this particular section, which is like a bonus section. Although it is not, really related to the scale theme, it is still something that is really relevant in today's time. And a lot of our clients who we do forecasting for, right, have asked us to adjust their forecast to kind of, include the COVID impact. And we as a company have done multiple innovations, like using government stringency index or recent demand or things like that. But other than that, there is one other theme or ever prevailing theme of such times, which is uncertainty, because that's the only thing certain right now. And that is why I want to push the case for a probabilistic forecast. So we've always been trained to think of forecast in a point forecast kind of a way, so that we say that my bike demand for this particular station at this particular time is going to be 3. But if you think about the application of it, or if you think from a different standpoint, wouldn't it be better that if the person who has to take that action to send that bike, or the strategic manager who decides to find out whether you need to make a new factory two years down the line or not, have more information to work with? So is it better that he thinks that yeah, so there's a 90% probability that my demand is going to be less than 120, rather than saying it's 100? So that is why I'm pushing for something, a probabilistic forecast, because it gives a much richer information to the end user, and it's easier. It gives you a lot of flexibility to take the correct action at that time, and it also kind of recognizes the uncertainty in the world and takes it into the model in some way also, so that it is truer to the real world scenarios. There are a few ways. There are a lot of ways to generate probabilistic forecast. We'll just take a few of them. So one of them is called the prediction intervals. So by prediction interval, what you'll get is instead of having 100, you can have 2 numbers, which is like the upper and the lower limit. And our statement would be that the forecast will be between these two 80% of the time. So this kind of a probabilistic output we can get from most of our classical time series methods, because they have strong assumptions associated with it, like it has to be Gaussian and the residual has to be Gaussian. So it's possible to calculate the prediction intervals based on the residuals for all of our IDMAs and exponential smoothing. Another way that we typically can use is to use quantile regression. So instead of predicting a point estimate with a single model, we have multiple models trained to predict each quantile in the distribution of the output. And one of the examples is in scikit-learn. There is the gradient boosting implementation, and there is a loss inside called quantile loss, which does exactly this. It gives you a probabilistic output. There's also a very less known library called SK Garden, which also implements a few of the quantile regression kind of methods. And another way that we can capture uncertainty is by using an ensemble of models. So if you have multiple models predicting the same quantity, and if there is a difference between them, right? Intuitively, you can think of it like all of these guys have some kind of disagreements about the output. And if everybody agrees and the forecast is like really close, then that uncertainty is very less. So we can use that kind of a modulation to kind of figure out the uncertainty. So for example, in the random forest, if you have 100 trees, instead of just taking a predict of the random forest, you can just get all the trees inside, make predictions on each of them. Then you get a lot of values, right? A list of 100 values. So instead of taking a mean of it, you can just take the median or the different quantiles to find out a little bit of a probabilistic output. And another way is to have a full probabilistic distribution as an output from the model. So typically our models, regression models, are outputting a single number, which is the number, which is what we want to predict, right? So instead of that, it's also possible for the model to output the parameters of a distribution. So any probability distribution, right? It's actually defined by a few parameters. So for example, the normal distribution is completely defined by the mean and the standard deviation. That is the only 2 things that is required for that distribution. So instead of predicting 100, if we assume that the output distribution is normal, we're going to predict 2 parameters: the mean, which is probably 100, and a standard deviation around it. So in the machine learning world, there is a newer algorithm, which is the NG-boost or natural gradient boosting. It comes under the gradient boosting kind of framework, but it has a probabilistic output coming from it. And then there is another library called GluonTS, which is built on MXNet, and Amazon Research is the main driving force behind that one. And it implements a lot of these, how do you say, RNNs and transformers, sec to sec, all of these models, but the end output is always a probabilistic output. So those are two libraries that you can utilize to kind of get probabilistic predictions. And another way is to go completely Bayesian. So when I say completely Bayesian, what I mean is, so suppose you have an equation, y is equal to ax plus b. Sorry. So typically what we do is in regression, we estimate a and b, and we have a point estimate for it, right? We have 3 and 4, for example. But instead of that, if we estimate a and b as probability distributions itself, then what that gives you is, by extension, the output is also probabilistic. So that is a Bayesian model or Bayesian way of doing it. It's computationally more expensive because you need to do multiple MCMC trials or Monte Carlo Markov chain trials. But it has been shown to capture uncertainty much better. And Bayesian neural networks. So neural networks is nothing but a really complicated equation with a lot of weights and biases, right? So instead of having point estimates for all of these weights and biases, if you have probabilistic outputs for all of these parameters, it becomes a Bayesian neural network, and it will do the same thing. It will capture your unpredictability better. There are a lot of methods. So PyMC3 is a library. The oldest and the most popular one in the probabilistic Bayesian probabilistic model kind of a scenario. And then there are newer libraries, Pyro, which is built on top of PyTorch, and TensorFlow probability, which is built on top of TensorFlow. So using all of these methods and more, we can have probabilistic forecast, which kind of includes uncertainty, or it doesn't run away from uncertainty. And that's the last message I want to leave you guys with, because we need to embrace that wisdom of the uncertainty and make it our friend rather than being scared about it. So yeah, thank you everyone. I think that's a wrap for the day, for the talks at least.
Yeah. Yes. So Manu, great talk. But we have a few questions before we wrap up the day. Let me start with one of the questions by Bharat. He is asking, application for the newer time series models. Any industries where specific time series models work better? I think this very much ties back to the question we had earlier on which is the best model, right?
Right. So I think more than the choice of the model, right? Most of the companies choose how they do forecasting based on a lot of other engineering constraints as well. So for example, Uber as a company is somebody who does forecasting at a massive scale, and the only way they're able to do it is because of so the things that we just kind of discussed, right? They have automated ways of finding out the models and parameters, and they mostly deal with pooled models. And even even the deep neural networks that they are training it on multiple time series at once, not just one single time series. So based on such things, right? If you have a large amount of data, huge amount of data, then your default or best choice would be to have deep learning based algorithms, which can handle a lot of these things together and still give you a good output. But if you are a very small scale, right, then it's easier to have like individual. You can look at each individual time series and find out the model that works best for it, and kind of take it forward. And then there are also a few intuitions that we can have. So if it is a very dynamic, so for example, in the FMCG or the CPG domain, right, a lot of the demand is kind of driven by the promotions that they run, the price incentives that they run. So if it is such kind of a scenario, right, then probably your multivariate forecasting works better than the strictly univariate one. So these kinds of intuition that we can have, but at the end of the day, we'll always have to kind of rely on cross-validated scores to kind of find out.
Right. Right, that's right. It's said. We have another question, and that's a very interesting one, Manu. You have to explain neural network to a non-technical background person.
Okay. So when you say non-technical person, are we going to say like a 5-year-old or somebody with an engineering background?
What we can do is, yeah, we can take both the scenarios. One is 5-year-old and the other who has some knowledge, but yeah, not very deep into it.
Okay.
Manu, this is Sid. You may want to come
Yeah.
on camera, at least
Oh
for
no,
30 minutes.
I don't have camera, Sid.
You don't have.
My,
Okay. All
yeah,
right.
my laptop doesn't have it.
Okay. Simple mercies, I suppose.
Yeah. So yeah, let's just take the engineering one first, probably. So anybody, I mean, let's not even go to engineering level, right? Let's take a high schooler.
Sure.
So you'll have, in high school, you have algebra, you have an equation, and you always know that okay, there is something like y is equal to mx plus b, which is like the ubiquitous slope equation that everybody learns. And so if you think about it, right, what that does is it kind of maps x or your input to an output, to a y. That's what that whole right-hand side of the equation does. So then we can just consider that as replace the entire thing as f. So then it becomes y is equal to f of x. So now then we can just generalize this f, this function. So this function right now it is mx plus b. It can be as complicated as you want, right? It can be say m cube x plus m square a plus b and everything, right? So just consider neural networks as kind of like an automated or a self-learning machine, which looks at a lot of these examples and kind of finds out the best f, that function, which maps y, I mean x to y. And how that that machine learning or the deep neural network learns is by looking at examples. So probably in 10th standard, right, in 10th grade, we'll have a lot of in your math textbook, there'll be a lot of equations. So you can actually have a training on all of those equations and find out the best possible mapping for each of these things, which is also kind of done recently. One of the researchers that came out of, I guess it was Facebook, which kind of solves an equation for you. It is trained on hundreds of equations, quadratic, I mean, all of these equations. And then it kind of, I don't know, it sounds magic when you say it, but at the end of the day, it's just a mathematical equation.
Right.
Yeah.
All right. Yeah, I think, yes. So basically understanding the functional forms and then to kind of probability based functional derivations of the different distributions and trying to understand what the distribution can be is where the neural networks and these help building those functional forms for us. All right. Let's move to the next question.
I guess the crux is not to be scared of neural networks, but just imagine it as another extension, a higher extension of high school math. That's the way Manu put it across, and that's the way it should be. I mean, we need to demystify these techniques, these algorithms for people at large. Otherwise, we're not encouraging people to come into data science. It's such an interesting profession to be in, right? It's given us so much.
Totally agree.
So why not let a lot of people partake in this profession. I mean, it's beautiful, folks, and the Manu's explanation of neural networks was one of the most lucid that I've ever heard in a decade or so. So Manu, and I really mean it.
Yeah, thanks it.
Okay. So there are a few more questions. Let's take that up. The next one is another interesting one, and the person is asking about in the web traffic data where there are peaks and troughs, but the predictions should the prediction consider them, right? So he's talking mostly from the web traffic data perspective.
Okay, so when just to make things clear, right? When you say that if you want to consider
which
them
model
predictions.
which model can be used
Okay.
for identifying these peaks and troughs? Yeah, that's what he's
Okay.
asking.
Okay. All right. So yeah. So my suggestion to you would be to, so there is a Kaggle competition which happened, I think, 1 or 2 years before, which is exactly on this topic: web forecasting, web hit forecasting. And the winning models were typically neural network based. I think there was a WaveNet architecture. WaveNet architecture is basically a 1D convolution architecture that kind of looks at your historic time steps and to get the forecast. And then there were a few solutions which used LSTMs, not in a straightforward way, but in a slightly convoluted way. It's very difficult to explain without a like a visual aid. But yeah, my suggestion would be to actually go and just read through the Kaggle forums of that particular competition. The solutions are well documented, and there's even ready-made code in GitHub for most of them. So you can, that should be a good starting point for you at that point.
Yeah, I think rightly said, Manu. I think Kaggle competitions are a really good way of learning machine learning.
Yes.
So with that, let's go to the next question, and this is I think again someone anonymous, I guess. Some simple models like moving average and best squares methods also give good forecast accuracy.
Yes.
Are these complex models really used in the industry, and how often?
Okay, so yeah, so that is correct. There are places where a moving average, a simple moving average, beats all of the sophisticated methods in the world.
Right.
So yeah, so basically what all of these different methods do is try and identify a pattern. And suppose if there is no pattern at all, it's like completely random, then moving average is the best thing that you can get, because it has less complexity. But on the same side, right? So identifying such time series that will not will not need a higher complexity of algorithms, that is the skill that we have to be gaining. So for example, as a data scientist or an ML practitioner, right, that is the kind of intuition that you should be having. And all of our time series segmentation that we talked about earlier kind of help you in doing that, to target such cases which you don't even apply any such algorithms. Even in our internal projects, right, we have multiple time series which are classified which like that, and we don't even apply any of the sophisticated algorithms there because we know it won't work. So that's the kind of knowledge that you've acquired after working with multiple clients. And the same thing on an individual level, you will get that intuition once you have worked with multiple problems.
That's right. And I think most of the people, when they start working, especially even the seasoned ones, the idea is to always start with the simple and then get to the complex, because that will kind of give us an idea of what is working and what is not working. And so start simple and then build to the complex ones. I think that's the way I usually do.
True. That's absolutely right. So the moving average model that you talked about, you can find, I mean, it's very easy to find out that one, and you can use that as a baseline model. So any model that is working worse than that, scrap it. Because yeah.
Yes. So let's go to the next question. And I will first take this one. Yeah. In how many ways you can check accuracy of a model? Is there any possibility we can achieve 100% accuracy in short-term demand forecasting, especially during the disruption or in normal times? This is by Naveen.
Okay, all right. So Naveen, so there are a lot of different ways of calculating accuracies, and again, there is no right way of doing it because each of them has its own advantages. So you have MAPE, which is mean absolute percent error, right? So I'm talking about typically in the forecasting sense of things. So that is something that is really intuitive. So if you hear a MAPE of 40%, you intuitively know that okay, this is 60% accuracy, and you know that it's okay. But there are problems with MAPE. First of all, if your denominator, you divide by actuals, right? If there is no actuals or actual sales, the ground truth is 0, then that whole thing becomes an infinity. So it's very difficult to manage such things. There are obviously weighted mapes, which are typically more used in the industry because that's more oriented towards action. So when you're doing a weighted map, what you're saying is, I am more concerned about the accuracy that I get on my high selling items rather than the smaller ones. So that is a better metric and usually the one that people use everywhere. Then we do see there are a few other methods like MASE, which is a scaled error, which kind of puts the benchmark as the naive accuracy or the very baseline model as a benchmark, and then finds out how best our model works better than that. So these type of things can be also used to kind of show your customers that how well your model is doing. And what was the last part of the question? There was one more question. Right?
Yes. Yeah. 1 second.
Yeah.
Yeah. So
100% accuracy. Yes.
Yeah, 100% accuracy.
Yeah. So Naveen, sadly, that's not. Yeah, you will never find that.
Yeah. So
even
I think.
Yeah. Even in times where there is no apps, I mean, there is no COVID and all, even in normal times, like good times, even then you won't get 100% accuracy. So
yeah. So with that, there are a few more questions, but I think we have kind of exceeding our time limit now. So we'll answer to you on
offline.
Individual manner. Yes. And I will hand it over to Sid for the next session.
Thank you, Kumar.
Thank you.
And thank you, Manu. That was a very lucid talk, and I think you managed to demystify demand forecasting and neural networks, for a lot of folks out there. Okay.